Okay, good morning to everyone and welcome to the 12th session of the Probabilistic Machine Learning Reading Group. Today we will be talking about diffusion models, and for that we are lucky to have here Alberto Suarez, who is a full professor at the Computer Science Department of the Universidad Autónoma de Madrid. So with that, the floor is yours, Alberto. Thank you so much.
Well, thank you very much for the invitation. And well, the topic we're going to discuss today is diffusion models for generative AI. Basically, have taken chapter 24 of Murphy. I think that's the book that you're following. I've covered almost everything in the slides, but I won't be able to cover everything today during the session because there's too much material. And I've also chosen to enlarge the presentation with some material that is not in the book, but I think it's important, and it's contained in the tutorial by Song that I will show you a little bit later. And so this is a selection. So, if you're interested in particular topics that I'm not covering, please ask questions. I think it's better if you try to ask the questions while I'm making the presentation. And of course, there will be a round of questions at the end, but I think it's useful if you can ask the questions also while I'm presenting the material, so that, everybody is on the same page. I'm having a little bit of trouble with the animation, I think. This is probably a conflict between Zoom. Okay, so this is a problem. Okay, here. So the goal of generative, I'm sorry, but I think I cannot hide things because otherwise so if it's in the way, I apologize. I will try to put it maybe, I don't know, how can we put it on the side? Yeah, if I had it, I don't know, for some reason. Okay, I'll put it up there where it doesn't bother that much. Okay, so the idea is that we have some data. I'm going to assume that this data is a uniform, an IID sample from some unknown distribution. And for instance, this data can be images of cats, and the idea is to find a way of generating new samples from this distribution with similar statistical properties, or not even that. Basically, I just want samples from these pixels. Here you have pixels, so in such a way that a human mistakes that combination of intensities of pixels with the image of a cat. So it's not even a mathematical problem. It's just it has some mathematical elements and it has some perceptual elements. And I'm going to focus, of course, on the mathematical elements. The idea is that you could actually make a parametric model for your PDF, but that's going to give you results that are probably it's not easy to train those models, but also sampling is going to be costly. There are some computations that are going to be incredibly heavy, like such as if normalization constants, things of that sort, that make it not worth directly learning the PDF. So I'm going to try to find indirect methods of sampling from this PDF without actually making an explicit model of that PDF. These type of generative models are implicit, since we don't make explicit model for the PDF. And we're going to focus on implicit models that are of the diffusion type. And I will justify later on what the name diffusion means. Typically, what we're going to do is to start sampling from some easy to sample distribution and a structured distribution like the Gaussian. Here, for instance, I'm showing an image in which each pixel has been sampled from a normal distribution independently. So of course it's noise and you don't see anything. And my objective is from this sample, I'm going to define a temporal process that goes, and the animation doesn't work. Sorry, but I'm having trouble with Zoom. Okay, there's an interaction there that doesn't work out. Okay, we'll have to do it this way because it doesn't work with the arrows. Okay, so the idea is that I'm going to start with this noise distribution, and I'm going to define a temporal process in such a way that gradually you will see a cat emerging from the noise. Okay, so this is a difficult process because I have to start with pixels that are absolutely uncorrelated. They're Gaussian, so they're independent because they're uncorrelated, and then I'm going to start trying to um, pixel at the pixel level manipulate their intensities in such a way that eventually I get the image of a cat. Literally, this is sort of a realistic a snapshot of what's going on in this denoising process. Okay, so how do we do that? We first are going to inject noise. Injecting noise on the image of on the cat is very, very easy. You just take at each pixel and you just add some Gaussian noise to the pixels. If the noise has a small intensity, you will see a blurry cat. And then as the noise intensity is increased, I will see a cat that's even more blurry. And eventually I will just lose all reference to the original cat. And this basically is indistinguishable from a sample from just Gaussian white noise. Um, Now, the process that I'm going to do is try to invert time. So we are going to do a time reversal, and I'm going to start with the noisy image and try to guess what noise I have injected to get from this image to that image. Remember that the noise injection is easy. You start with initial cat, you just add random noise until the noise is sufficiently large so that it obliterates the original image. And now what I'm trying to do is from this noisy image, I'm going to try to guess at what noise I injected from this image to that other one so that I can recover the less blurry image. The idea is you have a noisy image, then you remove some noise, you get a blurry image. You remove more noise, you get a less blurred image, and less blurred, until you get the image of a cat. Um, in this case, I just taken these photograms of a movie and reverse them. So I get exactly the same cat. This is assuming that I can actually learn the exact noise that I have injected. But what we're going to do is not to learn the exact noise, but learn which type of noise, which properties does this noise have to have, so that when I take it out, I end up with an image not of the cat that I perturbed in this first noise injection, but another cat, another image of a cat. Okay, that is statistically similar to that one. So in all the methods that I'm going to present today, there's a forward process, which is the noise injection process, and a reverse process, which is noise removal process. The noise injection I'm going to use to train a neural network that will actually learn how to denoise. So in fact, I'm learning a neural network that controls this reverse process. Okay, so that's this image here. And the first type family of models is going to be a discrete time Markov process. These are the first models that were introduced of this type. However, this is not my favorite models. I prefer the continuous time, and we will also go to continuous time. So in this case, we have a Markov process in the forward direction and in the reverse direction. The idea is that you start with one of the images of your sample of images of cat, and you apply this transition kernel. And you see that this is just a Gaussian. So the idea is that, let's say that you start at t equal 1. So x0 would be the original cat. And then you generate some noise from this Gaussian distribution that is centered at the image of the cat with some standard deviation. Okay. And then you inject some noise with that variance, which is basically diagonal covariance matrix. Okay. And that's your new cat. Okay, so basically each cat is a Gaussian perturbation of the previous one. And then for the reverse process, you also have a Gaussian transition kernel. This theta is going to be the weight of your neural network. We will see how to determine those weights. Only now the Gaussian doesn't have such a simple mean as this one. It has a complicated mean. So actually this sigma square could be beta t. So even though that's a hyperparameter that you could change, in some cases you just use sigma t square equal to beta of t. It doesn't really affect very much the quality, or it could, it probably does affect, but it's a minor improvement if you want. You can just use beta t here as well. So the noisy part is the same. What's different is this mu. This mu is a very complicated function that basically tells you that, let's go to this last denoising step. It tells you that in the eyes, if you manipulate a pixel that is here, you also have to manipulate a pixel that is, let's say, 10 centimeters wide from this other one, so that, the eyes are symmetric. So that creates spatial correlations that are quite complicated to model. Okay, all that information of, what is the spatial correlation, or what is the spatial structure of a cat image, is encoded in this mu. Okay. The key here is that instead of going directly from noise to the original cat, you sort of break up the generation process in small steps. Okay, the finding the mu that would take you from here to here is really complicated. It's not an easy process. However, finding the mu that takes you from here to here is an easier problem. So you've broken up a difficult problem, which is generate the image from noise, into a sequence of simpler problems that are related sort of statistically in this way. And the idea is that here you see that there is a dependence on t. So basically the type of manipulation that you have to do here is very different from the type of manipulation that you have to do here. Here, if you want, you just have to concentrate sort of on broadly getting a sort of a blur in the middle corresponding to the cat, but to outline the shape. I mean, there are no details. So this is just basically denoising a little bit, okay? And here you already have the cat. The only thing you have to do is that the cat looks a little bit grainy, so you have to remove the grains. So here is a refinement type of denoising. So this is more a global denoising, and this is more a detailed denoising. And that should be captured by this model of the conditional mean here. Okay, so now it comes the mathematical detail. Please let me know if this is over. And I don't know if you're familiar with them. So, but anyway, I'll start. And the way to let me know whether it's too easy or too hard is to ask questions. So I'm not seeing who is asking questions, just, go into the conversation. I will try to pay attention. Okay, so the forward process is the easy one. That's the one in which you have noise injection. Whenever I say X0 is a sample from P0, do not get confused, because I don't know P0. I just have a sample of the original distribution. This is just a short mathematical notation to say this X0 can be any of the images that I have for training, okay? And if you look, this is a discrete time process, so it looks like an AR1 process. The idea is that this is the image at time t as a function of the image at time t minus 1. Okay, and basically I'm injecting noise with variance beta t. This is diagonal noise, okay? That is to say the covariance matrix is proportional to the identity. And this square root of 1 minus beta t is just to make sure that in the limit when t goes to infinity, this goes to a normal 0, 1, okay? So the idea is that this is an AR1 model that is stationary. I choose beta so that it's stationary. And asymptotically, it will just blur the cat, the initial cat, into some realization of this Gaussian white noise, okay? And this is the limiting distribution is independent of X0. Of course, I'm never going to get to t infinity, but the idea is I generate t steps, and I hope that if t is sufficiently large, the memory of the initial conditions will have decayed. Now, we know that this is an autoregressive process. So actually, memory of the initial conditions decays exponentially. So it should be relatively easy to have a simulation with t large enough so that the sample that I generate at capital T, x sub t, is indistinguishable from a sample from the actual limiting distribution. Okay, so this is a stepwise procedure. So I'm going here 1 to capital T, but it turns out that the AR process, the AR1 process that I'm actually describing, writing down here, has an exact solution in the sense that I can simulate from xt starting from x0. Here I'm simulating xt starting from xt minus 1, the image before. So this would be, I have this one, I simulate that one, starting from that one. From that one, I simulate that one, etc. So that would be the AR1 process. But what I'm saying is that there is, because the form of this AR1 process is simple, I can go directly from here to, let's say, here. Okay, so I can inject noise directly to that point. Another thing that I want you to think of is that actually in the forward direction, larger times imply larger noise. So actually, it is, you have to think of progressively injecting more and more noise. Okay. So that is basically the formula to do the simulation in one step instead of doing it from t minus 1 to t. Here I'm just doing it from 0 to t directly, and there is a different coefficient here and a different coefficient here. Basically, those coefficients can be calculated in terms of the beta. I define some auxiliary quantities, alpha of t, okay, which is just 1 minus beta, and then the alpha bar of t is just the productory of these. This is just the result of a composition of Gaussians. Okay, so that's not very difficult to derive mathematically. Okay. Now, the reverse process is, as I told you, very similar to this one, only here, instead of a square root of beta of t, I have sigma of t. And this is a hyperparameter. You can use either the same expression, the square root of beta of t, or you can use some other expression. Again, it doesn't really matter much which function of time you're using here. Of course, beta of t and sigma of t have to be deterministic, and they have to be chosen by the user. We'll be speaking about different choices of that schedule of noise injection. This is sort of, it's called the schedule of noise inversion, and you use the same schedule in the reverse process. Okay, so what changes here is that in the forward process, the drift term, the term that determines on whatever happens at t minus 1 is very simple, is linear in xt minus 1, whereas here it's going to be very nonlinear. Remember that this is a backward in time process, so I know x of t and I want to generate xt of minus 1. And the goal is that I run this loop backwards, so I start at capital T. At capital T, I generate from the limiting distribution of the forward process, and then I decrease time, I decrease noise, if you want. And even though I'm injecting noise, I'll make a comment about this noise injection. Why is it useful? But this is basically what I was trying to guide the pixel intensities in such a way that if you have an eye at a given position at the corresponding other eye, you have basically the same intensity, so that the eyes are symmetric. So this is a complicated thing. You're trying to control pixel by pixel what is the intensity, so that the eyes of the cat look realistic. Okay, so that's a complicated control term. Okay. Okay, and your hope is that if this is well trained, and this has been properly trained, and T has been sufficiently large, so that you're guaranteed that you can sample from the limiting distribution of the forward process, then you expect that sorry, this is a mistake. this should be x0 condition to xt goes with p0. I'm sorry. I will correct this and send you the corrected notes because there will be some bad typos. So this is x0 condition on xt, okay, on the value of xt, should be something that resembles a sample from the distribution of cats. Any question up to now? Okay, so what we have to do is try to understand how can we define, how can we determine the values of these parameters. Okay, and here there's a lot of mathematics. I'm not going to really go very much into the mathematical details, except if you ask, of course. But since everything is Gaussian, it's really easy to write all these distributions. The transition probability kernel, as we have seen, is this one, okay, a Gaussian. This is the variable of the Gaussian, and this is the mean of the Gaussian. So I'm generating x of t, the image, with a t level of noise from the image with slightly less noise. T minus 1 is the slightly less noise, okay? If I want to model the joint probability for the whole trajectory, since at each step I'm injecting independent noise, this is just a product of all these Gaussians that I have generated in these t steps, okay? If I want to look at the marginal distribution of not the whole trajectory, but just the last point, let's say in the trajectory, one of the particular points in the trajectory, I will have to integrate over all the other variables. I get this Gaussian, which of course corresponds to these dynamics here. Okay. Oops, oh, sorry. And finally, one interesting thing, although I'm not going to use this fact, if you write down what is the model that you're making for the probability density of the noisy images. So x of t is the images with t, a noise with this proportional, that is not proportional, but monotonically increasing with t. Okay, so that would be the density distribution for noisy cats. If you do the mathematics, you're actually modeling this by a mixture of Gaussians. Okay, so you're basically taking the intensity of the cats at each of the pixels and just broadening that distribution. Instead of a delta, you just get a Gaussian there. So you're actually approximating things by mixtures of Gaussians. You don't use that fact, but I just think it's an interesting mathematical observation. Okay. Now, the cartoon that you have here that comes from the book is actually an image with a single pixel. Watch out, because here it's a little bit confusing. When you see this is not the image. This is just a single pixel of the images. So here you would have just images that either have, they will tend to have pixels with these intensities. Either when you sample from this one pixel image, you either get this intensity, let's say a rather black image, not completely black, but it's slightly black, or a brighter image here in this mode, or images with sort of average intensities. So images around each of the modes would be typical of this P0, okay, your data. And by the noise injection, you're basically transforming this distribution into a distribution that's less complicated, and eventually you end up with a Gaussian if you have actually injected a sufficiently large amount of noise. Okay, so that's the idea. To reverse the diffusion, you start, again, these are one-dimensional images with a single pixel. If you generate images here in this space, basically you would get most images would be gray, right? Because that's the mode of this Gaussian. And then some will be rather dark, but not very frequently because you are at the tail, or very bright. Okay, most of them will be sort of gray in the middle here, and the idea is that you are trying to apply a process that sort of goes back to the original one. So let's say one of these images that you may have generated here, maybe go to that image or to that image, to that image, to that image, and you hope that you end up in one of the high probability um, points here. Okay, so you start in, let's say you start at the mode, you expect that you end up at one of the modes. Okay, that would be sort of the idea. It's true that it's a
And
noisy dynamic, so you don't need to end up at one of the nodes. But let's say if you high probability start here, you will end up in somewhere with high probability. That's sort of the idea. Yes.
Alberto, can I make a
Yes,
question? Yeah, so
please.
thanks. How does this reflect? I mean, the fact that in an image of a cat, I don't know, brown pixels are close to brown pixels and black pixels are close to black. I mean, this is just. I mean, if this picture is not reflecting this like correlation of, right?
Okay, everything has to be there. I
Right.
don't put any prior on because I don't know if I interpret your question correctly. Real world natural images have a particular structure. So if you think, for instance, that you're actually modeling images from a comic book, let's say, in which everything is sort of contours and then flat color surfaces. Those images are obviously you need your images are going to be basically flat color surfaces and then abrupt changes, for when you change. That's a comic book image. Okay, in these in the original formulation of these models, nothing is assumed about the images. So you want to have it doesn't. You have to learn that. Okay, this mu has to be complicated enough to know that if you have a brown pixel here, that the nearby pixels are also brown, except if you're close to the edge. And again, I mean, imagine that you're also drawing a cartoon of a cat. What you would do is just basically put two eyes, a mouth, and some like a bowl for the head, and then some ears. Those 2 points for the eyes have to be also in specific positions. So this mu has to be sophisticated enough to know that if you're a particular position, approximately, let's say a cat has eyes at the distance of 5 centimeters, the corresponding distance you should have an eye also. Okay, so the neural
Okay.
network here has to be very sophisticated to learn that.
Okay.
But I think there's room for improvement if you know that your images have a particular structure. Okay, but from what I'm presenting here, no particular structure is assumed. Okay. So, okay, mathematically, everything is very clear, and you can do a lot of mathematics, and it's very interesting, etc. The problem is that I'm not going to use exact expressions here. For instance, this is the exact expression for if you had these mu tilde here and this beta tilde, which beta tilde you can compute because you can write it in terms of the alpha t bars, the beta, and the alpha t's. Okay, so it's here actually the expression of beta tilde. If you could compute this quantity, everything would be solved. Okay, but the problem is that this quantity has a dependence on x0, and this x0 is not known. So I'm not going to be able to construct this quantity. What I'm going to do is to basically make a model. Let me see where the model is. Yeah, make a model in which we don't have any dependence on x0. It will be sort of an average of these over all possible values of x0. Okay, so I'm going to replace these, which would be the exact quantity, by something that is parameters in terms of these parameters, and these parameters I'm going to learn from a neural network. Okay, technically the training goes through the elbow. I didn't put it here, but yeah, here I'm just doing basically transforming likelihoods. So this would be one of the terms in the likelihood of the model, okay, given the data. So x0, you can think of any of the original cat images, and this is just one term that would appear in the likelihood. Okay, so I have to find the theta that maximizes basically the expected value of this quantity over P0, when X0 is distributed according to the original P0. Okay. I'm going to use the elbow, Jensen's inequality, to get the elbow here. And again, this is all a complicated but straightforward manipulation. And the important thing is this quantity here. You end up getting a sort of Kullback-Leibler divergence between what would be not the conditional probability of the image with less noise when you have an image of higher noise and you have the initial image. Okay. Now, again, this quantity you don't have because this is the inversion of the this is this quantity here that depending on this new tilde. I mean, you do have for a particular x0, but you don't have in general for any image. So what you're going to do it is approximated by this model, okay, which is a model of the backward kernel that depends on these parameters. Here, the dependence on x0 is implicit; is no longer visible. Okay. Now, if you go through the mathematics, basically you want to have this quantity mu tilde, which is the exact one, being approximated by this other quantity, which is related to this model that we had for the backwards, the reverse process transition kernel. Okay, and what's interesting is that if you look at mu tilde, it has this form. Okay, so mu tilde is basically the noisy image minus some coefficient that is known because beta of t is known and alpha of t is known, is something that the user, the one who's doing the modeling, has specified. It's a deterministic function of time. And here is the noise that you injected into x0 to get xt. Okay, so in the forward process, actually to get xt, you would have x0 generate epsilon t, which is a sample from a normal 0-1 distribution, multiply by that, and then add it to x0 to get xt. And here what we're doing is removing that noise. Of course, I cannot remove exactly that one because I don't, if I start from xt and I don't know that, I don't know how to remove that. But I can approximate that noise with a neural network. Okay, and the idea is that I'm going to try to model the noise that I had injected into x0 to get xt. So from this observation, in the Kullback-Leibler divergence that appears in the elbow bound of the likelihood, you're going to basically the only mismatch is going to be related to the difference of means here. Okay, that's the only mismatch. You can show, just applying the Kullback-Leibler divergence between Gaussians, because that's what these are, okay, that actually that term corresponding to the mismatch between the means is just the mean square error of these epsilons, the true epsilon that you have injected to perturb the original image, and whatever prediction comes out from your neural network. So eventually, if you want to predict that error, what you could do is, for instance, a UNet type of model. Okay, in a UNet, you would have, if you use the UNet for autoencoding, the input and the output would be the same. But in this case, you don't want the input and the output to be the same. You want the input to be the noisy cat with noise level t. You have to tell also this network what the value of t is, okay? And from these two, the network's role is to try to guess what noise was injected into x0 to get xt. Okay, that's your training objective. Is just going to be the difference between the true noise that you've used to generate xt from x0 and the output of the network. Okay, there is some technical problems about how t is going to be. Remember, t is a scalar, so if you introduce it as a scalar, that's a very poor, very simple representation. So you have to do some encoding to enrich this input of t. Typically, you do some either sinusoidal positional encoding or random Fourier features with some frequencies that you sample from a Gaussian. And then there are these fully connected layers, and these layers are trainable, if I remember correctly. Yes, they're trainable. And the goal of these layers is to get these embedding to have the right dimensions so that they can be input at each of the stages of the processing from the UNet. Okay, now if I go to the songs tutorial, you can see what the UNet looks like. Okay, the UNet is just this one, something similar to this one. This is for diffusion models with continuous time, but the idea, is that you have this self-embed here. I don't know if it's large enough. Just a second. This self-embed is basically embedding time. Okay, this is basically Gaussian Fourier projection. Okay, that's sort of the time embedding for to enrich the representation of time. And then there are some convolutional layers because we're going to of course we're dealing with images, so we do have to do conditional layers, some dense layer, some group normalization. And I think in this case, if I remember correctly, the time element is included at each of these levels just by addition. By simple addition, you add time, the encoded of time, to each of the pixels of all the channels that you're actually generating. So that could be one way of incorporating the information about time. Another way is to modulate the group normalization layers. Okay, that's another way, which is a little bit more sophisticated, apparently. I don't have much experience with, which architectures work better, etc. Okay, so that would be just a typical UNet that you would be using to this end. Okay. So in fact, summarizing all the mathematical detail, you end up with a loss function that is basically an average, two averages basically, one over the initial images. This one, of course, you would do it with mini batches, just take a mini batch from your original sample, and then just the sample average over that mini batch. And these are epsilon. This is the noise that you use to corrupt the image. Okay, and then your goal is to minimize this norm. This is the actual noise that you have injected into the images in your mini batch, to each of the images in the mini batch. And this is the prediction of the neural network, and you're going to try to find the theta that minimizes this quantity. Now, this lambda of t is this complicated expression that is complicated but easy to compute. Remember that beta of t is something that we know, alpha of t and alpha bar of t is something that can be computed in terms of beta. So it is a number just as a function of t. So that's deterministic. However, what people do in practice is that this doesn't work very well. They just take lambda t equal to 1. Which is gives you even simpler loss function, which is just basically the mean square of your prediction. Okay, well, predicting just the mean square is easier than predicting this quantity, which is the one that you derive from the elbow. Okay, remember we were trying to maximize the likelihood. We wrote it in terms of maximizing the elbow, and by manipulating, since everything is Gaussian and the expressions are relatively simple, you end up having this quantity, okay, or a collection of these quantities. These quantities for each of the time steps, okay? what we've done here is actually average over time, assuming that time is a uniform random variable in 0, 1. Okay, here the book and I are being a bit sloppy because, of course, the process that I described was in discrete time. So you have to think of these as just taking one of the possible times of your discretization. So it's not very important that I'm sort of mixing continuous and discrete, provided that you keep in mind that this expectation is actually over discrete time steps. No, sorry. The formalization is with discrete time steps, but we actually do it with we do it with discrete time steps. So this is the pseudocode. Okay. So sorry about that, but I'm just using the sloppiness of the book, which is unfortunate, but it's easier to explain. Okay. So what is the algorithm? The algorithm comes from reordering all these expectations, which are all over independent variables. Remember, this is one of the images from your sample. So if you take a mini batch, you're just going to average over the mini batch. These are as many random numbers as from a normal 0, 1 as images, because here you will use this noise to spoil, to perturb an image. And here you're just averaging over time, okay? So the pseudocode is take one of the images from your training sample. For that particular image, generate one of these indexes, okay? 1, 2, up to t. So here it's actually using the discrete version. Third, you generate epsilon from a normal 0, 1. Okay, and then you input this quantity, and this quantity is just x of t. Okay, remember that we could go directly from x0 to x of t just by applying this formula with epsilon of t, sample from a normal distribution, 0, 1 normal distribution, in as many dimensions as pixels they have. Okay, so this is the output of your network. Okay, in the notes that I have included, I have tried to put the how do you call it? The parameters here at the end, not as a subscript, because I thought it was a little bit confusing as a subscript. Okay, so that is all you have to do for your gradient descent. And to generate new samples, you use just the output of the network to estimate that mu, which was controlling the backwards process. This is ancestral sampling, just standard ancestral sampling with this noise, etc. Okay, so this noise, it turns out that this is a sort of regularizing type of term, and empirically one sees that having noise here is actually helpful to generate good quality cats. So it's paradoxical, but noise is actually stabilizing this reverse process. And I think this sort of covers everything from discrete time. Now what we're going to do is to go to continuous time. So maybe it's the time to ask questions for discrete.
I have one really quick one. Do you have any intuition on why setting lambda equals 1 works better? Or is it just completely empirical thing?
Yes, the intuition is that basically this quantity actually, let me think, because I have to think. This quantity tends to weight with a higher value, a smaller, let me think, smaller or larger t's, smaller t's. Okay, so you're doing a really good job at refining. Okay, so you have a very strong signal for the backward process when you already have a cat. Okay, but the problem is that you need a very strong signal from the region where you have no idea of where the cat is. So basically, what lambda t equal to 1 is doing is giving equal weight to denoising this as to denoising that. You have to think, okay, this problem is much simpler, right? I mean, going from that image to that image is much simpler than going from this image to this image, because here, you know, you have a lot of graininess, and from the previous question, I mean, you see that here a white pixel can be surrounded by a black pixel, a brown pixel, something which looks very grainy. So here you have to, you're basically taking out the graininess, okay? So it's a much more complicated problem here, okay? And the lambda of t just gives more weight to errors that you make in this denoising, whereas here it doesn't give much weight. Whereas you really want to have a very strong signal here, because if you see, this is where the cat is being formed, okay? The rest is sort of refinement of the cat, okay? So the idea is that if you don't correct for that bias, that this function, well, that let's say bias, that insistence that you do the refinement steps very carefully, because the signal is very strong, because it's being amplified by that lambda. Whereas for t large, this lambda is very close to zero, and you don't have almost any signal. Okay, you have to compensate for that, and this lambda to 1 basically gives equal value to the reconstruction error as measured by this mean square error at every point in time.
Okay,
it's easier to see this in the continuous time. Okay, so if you don't mind, we'll go back to this question when we go to continuous time. Any other question? Okay, so continuous time actually starts, even though they're equivalent, I think historically was introduced from Langevin dynamics. And I think you've already seen Langevin dynamics, I think. Is that correct?
Yeah, we've discussed them a few times, yeah.
Yeah.
Okay, so remember that Langevin dynamics is, you define a continuous time equation, differential equation, okay, in which the diffusion term is just basically a linear process scaled with some quantity, whereas the drift term is complicated. This is basically related to the score. The score is just another word for the gradient of the logarithm of the distribution of the initial data. I'm putting here 0 to stress that this is the initial data, okay? Watch out, because this t is not the same t as the one that we were using in diffusion. It's a different t. I mean, you can think of a different time dimension that is orthogonal to the one that I discussed in the previous step, okay? The idea is that you can prove that no matter where you start here, whatever the value of x0 is, if you solve this stochastic differential equation, and since it's a stochastic differential equation, its solution has to be a simulation, okay? If you solve that asymptotically, you're going to get a sample from P0. Okay, that's the idea of Langevin dynamics. And what's interesting also is that that's independent of epsilon, provided that epsilon is large. Okay, the issue of how to choose epsilon is not an issue related to what is the asymptotic distribution, what is the limiting distribution of this stochastic differential equation. We know that the limiting distribution is P0 independently of what the value of epsilon is. In physics or statistical physics, this is called the fluctuation dissipation theorem. Okay, so epsilon really is a parameter that has to do with how well you can numerically actually sample from that limiting distribution, which is the one that you're interested to sample from. Okay, so that's Langevin dynamics. Usually, of course, you discretize, and you know this discretization actually is the connection between these continuous time models and the previous models. Okay, personally, I think the continuous time models are much more elegant and much simpler to understand. Murphy's book concentrates on the discrete time, and I think it's much easier to understand the continuous time. So I'm going to spend a little bit more time than the book in the continuous time. Okay, so the idea is, for instance, a typical illustration of this Langevin dynamics is that my target distribution, P0, is a mixture of Gaussians, and my initial distribution is a uniform distribution. So basically, this is a movie that is being repeated over and over. Okay, I will say when t is equal to 0, that will be the initial. Okay, that was t equals 0. So t equals 0, and then it evolves, and asymptotically, you see that the initial samples that were uniform in this square, they half of them go to this upper node, half of them go to this lower node, just because of the symmetry of the Gaussian, of course, okay, of the mixture of Gaussians. Now, if you want to make a connection with images, this would be an image with 2 pixels. Okay, so the intensity of the first pixel is encoded by the horizontal coordinate, and the intensity of the second pixel is encoded by the intensity, by the height, by the vertical height. Okay, so basically, what I want to generate, this P0, is images in which the 2 pixels are white, which would be where my red point is there. So all these points are all images that are in which both pixels are white, or pictures in which both pixels are black. Okay, that would be corresponding to this mode of the distribution. Okay, so of course, if you have an image which is 28 by 28 pixels, you would have to do this drawing in 700 and something dimensions, which is not possible. That's why I'm illustrating Langevin dynamics only with images of 2 pixels. Okay, so the score here, I mean, if you think of a physical system, this is basically dynamics of a particle with some heat bath. Okay, the Gaussian noise works as this thermal agitation type of motion that you see in the simulation. And this is a force field, and the score is basically a force field, and the force field is actually represented by these arrows. Okay, so you see that the force field, when you fire from one of the modes, is very strong. It brings you sort of in the direction of the mode. You see that it's not exactly in the direction, because of course there's some a curvature in this space, and you have to sort of, the gradient of the log PF is not a straight line here. You have some curvature to go to the modes. Okay, and you see also that the force field to the right of this diagonal is all attracting you to that mode, and the force field going to the left is attracting you to this other mode, etc. Okay, so that would be Langevin dynamics, but we all know that Langevin dynamics suffers from a lot of shortcomings. I mean, if you don't, here I've started in a very, very symmetrical initial condition in which the uniform distribution covers both modes, okay? And it covers them in a symmetric manner, so that, half of the points, the ones that are above this diagonal, go to that mode, and half of the points go to that mode. But if let's say that I make a mistake, and instead of starting with a uniform that covers the 2 modes, I start with a uniform that covers only the mode which is on the bottom left. Okay, with Langevin dynamics, even though I have a theoretical guarantee that asymptotically this will equilibrate and generate a sample from P0, what will happen is that initially the force field is so strong. If I'm close to this mode, the samples go to this mode, and then the thermal agitation, which is given you by the Brownian motion, little by little will lead to some leakage from this mode to this other mode. But to go from just thermal agitation to this mode to that mode is very unlikely. So if I don't start with the right uniform distribution that covers both modes, if I cover just one, I will just equilibrate to one of the modes, and then in a very, very long time scale, eventually, some of these particles that are, jittery in here, that thermal agitation, it's very unlikely, but there will be a large fluctuation that takes you to the other mode, and eventually this should be equilibrating. But that doesn't happen, okay? So one of the things, I mean, one of the problems is that, when you have, okay, so that's one of the shortcomings of Langevin dynamics. But also, if I don't have P0, because here, of course, I calculate these arrows because I have P0. If I don't have P0, if I have a model and I want to estimate from the data, it turns out that in the regions where I should have more information, which is, far from the modes, remember that I start with a uniform distribution in this square. So if I'm here, I would like to know what the score is to go to this mode here. Okay, here the target distribution is shown as shade of brown orange. Okay, the darker the brown orange, the higher the PDF of P0. Okay, the higher the value of P0. So you have two modes, one which is stronger than the other one. So I would like to have, more probability here than here. The problem is that if I'm here and I don't have those arrows, those black arrows. I want to estimate from the data. If I want to estimate it from samples of the brown distribution, the target distribution, all of the samples will be around the modes. There will be no samples here. So precisely at the positions where I need to estimate the scores better, I have no samples. So the uncertainty of my estimates here is very large. The uncertainty here is very small because I have a lot of samples. But you look at the arrows, they're so small that it doesn't really help very much because you're already sampling from the mode. So, you're going to get extremely good estimates where you have samples, that means here and here, and extremely poor estimates when you don't have samples. Okay, so how do you fix it? In Langevin dynamics, you say, okay, instead of using this target distribution, I inject a lot of noise, I perturb the density, and I learn this other one. Of course, I'm learning the wrong distribution, but it's wrong in a matter that is not arbitrary. It's wrong, but it has the same modes, at least, okay? So the idea is that, okay, I have samples from the Brown distribution. Most of them will be here and here. I take this sample and I just add Gaussian noise, okay? So I contaminate it with some perturbation. And instead of a point that was here, I perturb it and it ends up here. A point that was here, I perturb it and it ends up here. Okay, so that's what is represented with this one, okay? And now I estimate the score, not of the original density, but of the perturbed density, which should be a simpler problem because I have samples basically all the space, okay? If the noise is sufficiently large. Okay, so I have an accurate estimate of the score of the wrong distribution because of the perturbed distribution, okay? I would like to have that one. Again, it's wrong, but it's roughly, it's relatively along the direction of the true density, which is the unperturbed one, okay? So what I can think of is doing a simulation in which I make the noise progressively smaller. So I start with a uniform distribution of points, okay? And I make a simulation with that level of noise, okay? And instead of converging to the final distribution, which is this one, okay, with modes there and there, okay, I start with a uniform, converge to samples which are typical of the perturbed density, but you see that this perturbed density tends to have more probability precisely in the regions where the true density has more probability. I use that those samples from the perturbed, which are typical of the perturbed density, as a warm start for the simulation with lower noise. And you see that it's sort of the lower noise concentrates better around the modes, and then I lower the noise. So if I do this annealing slowly enough, I eventually am guaranteed to convert to good samples of the target distribution, which are, the ones corresponding. So this is high level noise, medium level noise, low level noise, okay? And this you can do with some score matching, some sliced score matching or something of that sort. And I'm not going to, this method is called Langevin dynamics. And what I'm going to present is the continuous time version of Langevin dynamics. And here is very similar to the other process that we had there. Okay, remember that we had a forward process and a backward process. Okay, and in the forward process, basically that was an autoregressive model, right? So here dx, if I want to translate it into my language, into the discrete time language, I will have to write this as x t minus xt minus 1. And then the xt minus 1 goes to the other side. So you would have xt equal xt minus 1 plus some term, okay? F here is known, okay? You will see that, for example, f can be 0, okay? Or f can be linear in x. And the one that is similar to the discrete time model is when f is proportional to x, okay? Just keep that in mind. But you could do a simpler model in which f is equal to 0. So let's assume that f is equal to 0. That's the simpler case, okay? So the forward process is just injecting Gaussian noise because that's a Brownian process scaled. That's a linear process scaled with some standard deviation that is actually g of t is increasing in time. Okay, that's sort of the idea. G of t tends to increase in time. Okay, so that would be the noising process. Only now this process is in continuous time. Okay, and the backwards process that goes from noise to the original cat also complicates the Wiener process term is the same. It complicates the term corresponding to the drift in this stochastic differential equation. Okay, remember, this is stochastic differential equation. The term corresponding to the ODE, which is this one, is the drift term. The term that is proportional to the Wiener process is this other term. Okay, so I'm inverting time. There's a theorem that tells you that if you put that, you're inverting time. Okay, now notice that this is a score. This is the score, but there's a difference with Langevin. This is not the score of P0, but it's the score of PT. So this PT is the density, the PDF of the noisy cat. Noisy and the noise level indicated by T. So these noise levels here, T1, sigma 1, sigma 2, sigma 3, correspond to larger times, larger, smaller, smaller. Okay, so this is the reverse process that I'm doing here. Okay, larger noise, smaller, smaller. Okay, so if you understand this, the scheme is exactly the same as with the discrete time process. Basically, you simulate forward, and the forward simulation, you can do it in one step, okay? Because I'm going to choose F in a simple way so that the forward simulation is very easy, okay? In the other one, I chose a Gaussian kernel. Here, I'm also choosing a Gaussian kernel, something equivalent. And the idea is to inject noise until the distribution of remember, x0 is the image at time 0 without noise. X of capital T is the image with a lot of noise. My goal is to make T as large as possible so that it goes to some limiting distribution whose form I know. And in general, is going to be the Gaussian distribution, okay? And then, provided that I have a good estimate of this score function, okay, which I will learn with some neural network, I can reverse the process. The forward process, I can do it in one step. The reverse process, I need to do a numerical integration of this stochastic differential equation. The initial condition, this stochastic differential equation is backwards in time. So I start from a sample of the limiting distribution of this forward process, let's say the Gaussian, a Gaussian with diagonal covariance matrix. So that's easy to sample. I integrate backwards in time from T to 0, this stochastic differential equation. And the idea is that, that's why I put a backwards arrow. The result of that backwards integration is some random variable that approximately some random variable that is sampled from P0, the original distribution of the data. So that would be a synthetic sample, okay? This is sort of the cartoon for an image with a single pixel, okay? So here, my initial data is either images which are bright, corresponding to images around that mode, or images that are dark, corresponding to that mode. Remember that this image has a single pixel, and this height is the intensity of the pixel. I do the forward noise injection, and eventually I just get gray images. So from white or black, I go to gray, okay? And the idea is that now I generate a gray image, and I steer the process with the score, the time-dependent score, okay? So that, for instance, I generate that gray image, I generate this backward process, and you will see that this backward process is actually bringing me to one of the areas in the pixel intensity where the PDF, the target PDF, has high densities, or around one of these two modes. Okay, that would be sort of the cartoon. Okay, here you have the same cartoon for the forward process. On the left is basically, instead of a one-dimensional model, what would happen with a true image. Okay, you start with the images, this is images of rooms, okay, and you're injecting noise, and eventually just get Gaussian white noise at the end. Okay, and the idea is that now I want to invert the process. Okay, I start with 4 particular values, which correspond to these 4 trajectories. Okay, and the score network, which is trained, is actually guiding the process so that it ends up at the right, at one of the modes. I don't know to which one it will go. I mean, notice that this one starts here, eventually goes there, but this one starts there, it goes there. At each time, this is stochastic differential equation. So you could actually start here and end up there. The idea is that you don't start here and end up here where you don't have any density. This is sort of sort of background colors are actually trying to represent the probability flow. Okay, so yellow is higher probability, green is medium probability, blue is low probability. Here you would have a Gaussian, so the yellow, which is higher probability, is in the middle. And then as you drive the system with your score network, your probability density starts becoming bimodal. Okay, and eventually, if you've trained correctly, you go to one of the images, basically, but not the original ones. Okay, some other images. Okay, so this is something I think that Murphy doesn't speak much about, which is the types of diffusion models that people use. And actually, they just correspond to different choices of F and G. Okay, but especially F, that's sort of the defining quantity. Okay, so the simplest one is variance exploding. And variance exploding corresponds to just injecting noise using Brownian motion. So it's a very simple stochastic differential equation. It's just the Wiener process multiplied by G of t. And G of t is, for instance, sigma to the t. And sigma is a hyperparameter. In Song's tutorial, sigma is 25, okay? Because they're going to generate images from 0 to 1. And 25 here was seen as good enough so that asymptotically you get basically you lose reference of the original image. Remember that in the forward process, your goal is that all the images eventually at time capital T are indistinguishable from Gaussian white noise. Okay, so, and I'm sorry because I think I'm taking a lot of time, but I'll be finishing soon. Okay. Okay, so what I was saying here, f is equal to 0. So it's very simple. You can generate samples from x0 just by calculating the sigma of t, which is the square root of this quantity. All this analytic. Okay, here sigma 25. So this is just 25 squared to the 2t minus 1. So this is something that you can compute. Okay, you compute that. You multiply by a sample from a normal 0-1 distribution. You add that noise to the initial image and you get the spoiled image. To go back, you sample at time 1, capital T equal to 1, okay? Sample from this normal, okay? Notice that this normal is not the same as that normal. And the idea is that you see that here you never lose memory of the initial condition. X0 is always there, okay? However, if sigma square is very large, and you see that if sigma is 25, this is 25 squared minus 1, which is very high, very large. Okay, what happens is that the noise that you have injected is so large, this term is so large, that basically there's no difference. It makes no difference if you just put this x0 equal to 0. These are the images which are whose pixel intensity is normalized between 0 and 1, and you're adding here something that is of the order 25. So you can imagine that this number dominates that one, and you don't even see the image. So in the backwards process, you sample from a Gaussian with that covariance matrix, corresponds to just putting 0 here, okay? Do the integration using, instead of the true score, the score that you have learned, okay? To learn the score, let me just jump into the loss function. You have to do something very similar to what you had earlier. This is the score net. So this is like the U net that you had before. And now what you do is this U net is used, multiplied by sigma of t, to model minus the noise. Okay, remember that Z is the noise that you have injected to spoil one of the images from the original data. Here, sigma S is learning minus Z. So you're actually learning how to denoise that you're using, okay? And here we've also used this infamous lambda t, okay? Now remember that sigma of t is growing exponentially. Sigma of t is basically sigma to the t, 25 to the t. So this is growing very fast, okay? If I just leave the lambda of t, oh, let me see. Sorry. Where is that? Yeah. If I just choose lambda t equal 1, you see that this is suppressing a lot, because sigma square of t is increasing the signal, the noise signal from large t, okay? So actually, we're giving too much weight to points that are with a small noise. And we want to give also large weight to time instance where you have injected a lot of noise. Okay, so that's the rationale of just forgetting about this prefactor there and just putting a 1 instead of this prefactor. Okay. Now I have little time because I think I'm way over. Yeah, I'm sorry, I'm way over. What's interesting, just one thing. Okay, it turns out that to do the reverse process, I don't need to do a reverse stochastic differential equation. What I can do is to write an equivalent probability flow ordinary differential equation. Okay, so in fact, even though I've described these, the reverse process, as also a stochastic differential equation, you could do the solution of a deterministic ODE. Okay. Now, this is advantageous because for stochastic differential equations, I have to use a numerical scheme which is Euler-Maruyama, okay, which is not particularly high order. It's a variant of Euler, and you know that for ODEs, the Euler scheme is too simple. In general, we don't use Euler. We use Runge-Kutta or some higher order methods. However, for SDEs, we don't have really the equivalent of Runge-Kutta. We can only do Euler-Maruyama. So it's a very poor, if you want, numerical approximation. That means that we have to use a lot of steps to do the sampling. So the sampling is relatively slow. If you use the ODE, which is equivalent, which you can show that is equivalent to the reverse SDE, you could actually use less steps in the generation part. Not in the forward part for training, no, because that dynamics are always stochastic, and actually, since you can do it in one step, the cost of the training doesn't have to do with the difficulty of integrating the stochastic differential equation, which is exact, but rather with how many epochs you need to actually train your score network. Okay, but going backwards, yes. I mean, it depends on how many steps you give. So if you have the probability flow ODA, you can make do with fewer steps. However, empirically, one sees that that's not a very good way of reversing this process. Okay, it tends to give images of poor qualities. So the noise in the reverse process actually improves the perceptual quality of the images, yeah, probably because of regularization type of effect. Okay. One advantage that this probability flow of the ODE has is that it can be used to compute likelihoods. The reverse SDE cannot be used to compute likelihoods because you're injecting noise. I mean, here you're injecting noise. So you're not, these dynamics do not preserve likelihoods, whereas these dynamics, since they're deterministic, okay, this is an invertible continuous map, actually preserves probability, follows sort of a Liouville type of equation, conservation equation. This is here basically in flow matching, because based on that observation, you can do something that is totally deterministic, which is flow matching. Okay, you can see that if you have the ordinary differential equation, you can actually get the PDF at let's say the PDF at some point in time in terms of the PDF at some other point in time. Okay, just by integrating over the divergence of the velocity field. In this case, the velocity field is just that quantity. Again, remember that we have chosen f equals 0. Okay, so that quantity is just minus 1/2 g squared of t times whatever comes out of the score network. Okay, so these computations are relatively easy to do. Gradient are automatic in PyTorch or in JAX or whatever tensorial autograph framework are you using. So all these things may be costly to compute, but they are doable relatively simply. Okay, the rest of the talk was devoted to variants of this, and I'm just going to mention the subjects, and if you're interested in, and if there is time, I will be glad to answer any questions. If not, there's always my email, or I'm not very far from you, so you can just stop by and talk. Diffusion tends to be more efficient in latent space. So what you could do is combine this diffusion model with some autoencoder. Okay, so you, for instance, here, this is an architecture corresponding to, I can't remember. I think this may be similar to what stable diffusion is doing to have very good quality text to image type of generative models. Okay, so here, for instance, the original image X is encoded into some latent space. Here in this latent space, you do the forward diffusion process, and then now you have a representation that is in the latent space that is noised. So this would be the forward injection process. And what's interesting about this latent representation, first is the dimensionality reduction. So you could, in principle, use simplet networks to learn how to go back. This is the network, the denoising UNet, that allows you to go back. So, you know, since all your generative model is in this latent space, you can make it more efficient, simpler networks, so easier to train, easier to generate, etc. But I think more important than that is that if your encoding is good, usually the latent space captures a lot of meaningful structure in your data. It's a little bit, trying to learn that the two eyes are at exactly 4 centimeters. Okay, that's a very, let's say, low level feature. If it's in a latent space, maybe there's something corresponding to I should be at 4 centimeters, sort of encoded in the sort of the latent space structure. So it's going to be easier to do things or incorporate conditioning information. Let's say that you want to incorporate, you do want to do a generation here that is conditioned on text or on style or something. It tends to be easier to integrate that image in latent space than in the original space. Okay, so and here you can use also attention layers to merge inputs from text, etc. So it's a little bit more sophisticated, and in practice, these types of models are the ones that give you better results, especially when you do text to image type of generative. The rest was just talking about how do you merge text and image, but we've already sort of discussed it here. Okay, it's not very different. There are different ways of doing it, but they're not very deep. Here you have examples of a model trained with IMINIST, okay, some particular model that is actually provided with the book, I think. I haven't checked at the code that's provided with the book, but I think this model is actually provided with the book. This is unconditional sampling. You see that, well, focusing on the digits, they're not bad, but let's say that these, you don't know whether it's a 6, an 8, or something like that. If you do class conditioning, which is B, okay, you get more clearer digits and letters. Okay, so class conditioning is good. Of course, there's the cost of how do you do the conditioning, either based on a classifier with classifier guidance or classifier free, etc. This is, for instance, directly conditioning on class label. The disadvantage of directly conditioning of class label is that you have to do one different model for each class label. So one model for the ones, one model for the twos, one model for the threes, etc. That's costly. And this is this classifier-free guidance, okay, which also gives you good quality. So you can actually, this is unconditional, condition on the class, and then some implicit conditioning, which is using the strategy that's described in this slide, okay? You can do this for hyper resolution. This is, for instance, the paper that describes Google's Imagen model. It's called like that in Spanish. You can also adapt diffusion models for discrete data, let's say text. Okay, for instance, this model D3PM has been adapted for text. The corruption here is not injecting Gaussian noise, but rather spoiling the text little by little. Okay, so if you think of tokens as words, which they're not, okay, but you can think of tokens as words. You can, for instance, permute a few words, okay, and that would be the text corrupted by permutations, okay, and you do a few permutations, and then you do more permutations, and that would be the noise injection step, and you would then learn a network to invert these permutations from a random text that basically brings you to a coherent test. Thus far, you don't have good results for text. It's not competitive with a standard text. And this is just a summary of what we've said. So thanks for your attention. I'm sorry that I've taken so much time, but there was a lot of material to cover. I hope it's not, you didn't have to go to something urgent.
Thank you so much, Alberto. Are there any questions?
I have one quick question, which in all the models that you have, the noise in step and the noise in, you always use a normal Gaussian noise. What happens if I don't know if it destroys the mathematical properties and stuff. What happens if you use correlated noise? Because, as for example, it has been asked before, the pixels that are close to each other, in the end, they are similar and have, I don't know if correlation. That's the question.
Yes, you could do that, but in practice, it's not really necessary. The reason is that you have to remember that the network that's learning either the noise or the score is a unit. Okay, so the first layer here is going to be a convolutional layer. Convolutional layers already know which pixels are close to your pixel. Okay, so this is an educated guess, okay? I don't have a demonstration of this, but I think that the fact that in images, the intensities of the different channels of nearby pixels tend to be correlated, is effectively captured by the first layer or the first few layers in the UNet. Okay, so that you wouldn't gain much by introducing more complicated noise. Okay,
Okay.
that said, I'm currently doing some research on this topic. So, maybe in a couple of months I can tell you whether this helps or not.
Okay, okay. Thank you.
And quick related question, would the same apply for videos? Because there you obviously have some temporal constraints and
Yeah.
temporal
I mean,
correlation, but that correlation
the,
is just learned. It's not usually imposed, I guess.
yes, yes. I mean, I think, videos are even more, how would I say, important, I think, to capture the continuity in time, because I mean, this is a very weird way of generating images, right? Because if you think of the noise generation process, so let's go here. Sorry, the generation process, you're basically painting pixel by pixel. So you're doing something very complicated. You're not painting the same way humans paint. Okay, humans paint like sort of a rough sketch, and then sort of try to, from that rough sketch, you sort of try to define detail. Okay, whereas here is basically you're just injecting noise at each pixel in one by one. Okay, so you have to be very careful about the correlations. So yeah, I mean, this you need some improvements if you want to take into account that in the video, the next photogram is likely to be very similar to the previous photogram. Okay, again, but that you could capture actually by the structure of the network. Okay, so convolutional neural networks have that bias naturally. Okay, so the network that you can use for video could also have some way to hard code that sort of continuity in time of the video image.
Okay, thank you. And also related to this, like what you just said about the way we humans paint, uh, would that also kind of explain the success of stable diffusion? Because I guess since you're using VAI for encoding, then you're more doing like a conceptual painting rather than like on the painting on the conceptual level rather than the pixel level, and maybe that's why it also works best. And if not, like, and also regarding that, why is not possible to do that for text?
No, I'm not saying that it's not
I mean,
possible to do it
why
for text.
doesn't it work well?
Well, why do transformers work well?
Okay, yeah, fair enough.
I mean, we've taken forever to find an architecture that worked for text, and it turns out to be transformers. But that doesn't exclude that there are other architectures that could work equally well. I mean, that could be also another topic. How do I define architectures that are adapted to text? It turns out that this type of reconstruction doesn't seem to be as nice for text as it is for images. Probably has to do with the structure of the noise injection. I mean, the noise injection I'm doing is inject Gaussian noise, and Gaussian noise perturbs the image a little bit. What I'm saying, okay, take a noise and permute words. Depending on how you define distances on text, that could corrupt very quickly the text. I mean, by permuting, let's say, okay, if you permute just two adjacent words, it could be okay. But if you just take one word and put it wherever in the text, it takes very little noise to just not be able to recognize that text. Okay, by a human, I'm talking about by a human. So maybe what happens is that the Gaussian perturbation in images is capturing some sort of a smooth degradation of the image, whereas the discrete perturbations that you need to do in text are much more abrupt. And to that, I guess you can argue, well, okay, but then embed the text in some latent space that is continuous, and then there you're doing some permutation in a high level representation that has some structure, so it's meaningful, etc. But I think that continuous representations of text are not easy to decode. I think that I'm not a specialist in text, so maybe some specialists can answer this question a little bit more carefully. But it's an empirical observation. I mean, we try things. Some things work best for images. Some work best for text. Okay, it's true, for instance, that transformer also work well for images. Okay, fine. I mean, that's an empirical observation. As far as I can tell, nobody got that by thinking. We got that by trying a lot of things.
Just a very fast question because we are over time. I'm really interested in these promising methods. Talk was overwhelming to me, but just one question, because I'm researching with electrical storage. So I'm saying it's a time series, just one dimension. And we are thinking in using methods like transformers or recurrent neural nets, even the variational autoencoder. What do you think about applying diffusion models which are so good in dealing with images or video, if it's applied to one dimension problem? Do you think it's worthwhile in doing so?
But I'm not sure what the question is, because I don't know what you want to do with the one
the problem is one dimension is just a time series of electrical storage, availability of batteries. Okay.
But do you want to make predictions, or do you want to generate?
Right, to make a forecast of the availability of batteries. Okay. So my study, my field basically is renewable energies, and that we need a storage to cover when we don't have sun or wind, right? So the point is, well, first the batteries degrade physically. There is a degradation, and that impacts basically the availability. And when you have problems with availability, your price change. And we want to focus finally the price of the battery, but that depends on the availability.
I understand the problem. I mean, the thing is that these models are not useful for that, because what I can do with this problem is, let's say that you have a collection of time series. Okay, I could generate a new time series that has statistical properties that are similar to the time series that you've given me. So you have just let's say in one day, in 24 hours, what is the time series of energy demand? Okay, and I have that for every day in 20 years. Okay, and I want to generate another curve that has similar statistics properties to that. So for instance, those type of curves should have peaks in the winter months and in the summer months, because in the winter you have to heat, in the I don't know, things like that. Okay, so you want to generate a new synthetic time series, then you would use a generative model. But if you want to do for a single time series, I have, let's say, 100 days of my demand, and I have 100 days for many years. Okay, and I want to predict 101 day prediction. I wouldn't do it with a generative model. That doesn't really apply. Generative models are basically to generate the time series itself, not the prediction of the next step. But what you could do is, for instance, use a variational autoencoder or something of that sort, in which this would be just this X. You can think of it as your whole time series. So, for instance, if you had a year of data, that would be the energy demand each of the days of 365 values of a particular year. That would be 1x. So let's say year 2026. And then you would have the same value for 2025, for 2024, etc., whatever. Okay, then you could do a variational autoencoder and express that X in this latent space, Z, okay? With the hope that here you capture in some meaningful structure, okay? And then here, in this space, you could train a neural network to predict the next day energy demand, okay?
Understand. Yeah.
Of course, you could train it here, but the idea is this autoencoding will bring it to a space where you have, in a natural way, patterns or properties, characteristics that are actually more better represent the properties of the data that are useful to make predictions.
Absolutely. Actually, the properties are spatial and temporal properties. The question is because there are today transformers that are able to work with time series in one dimension. There are many. Temporal fusion transformer or MBits by Joshua Benjo. There are many today.
No, but I agree. But what I'm saying is that prediction is different from the model that we are trying to address here.
Right. Okay. Thank you very much for the answer. Thank you.
Okay. So thank you so much. Thank you all. I don't know if there's any additional questions. We're past over time, so I think it's been a really valuable talk, Alberto. Thank you so much detail. And I think we're gonna love to reread the slides. It was a really interesting talk. So
okay,
if there's any other question, yeah. I don't think so. Maybe no.
Thank you. So I'm sorry I didn't put my email, but it's alberto.suarez@uam.es. Okay, for those of you who don't remember, can't remember, you can ask David or
yeah. Okay. Yeah, we can send it. We can put it in the email we send after this. So yeah.
Okay.
Thank you so much.
Thank you.